Hey guys, and welcome to this video on the closest approach of two particles, part 2. This is going to be the scalar product approach. We're going to look at the exact same question we used when we looked at the calculus approach, and we're going to look at the differences between the two methods. Now this method is a little bit more involved. I think that you have to be more of a visual person to understand this method, and if you are not someone who's very visual, I would stick to the calculus approach. Alright, so we've got two vectors A and B, and we've worked out that the position vector of those two particles can be given by that vector and that vector. So the position of the first particle is defined by the yellow equation, and the position of the second particle is defined by the blue equation. And obviously, this particle is going to keep traveling in that direction, this particle is going to keep traveling in this direction. So the way this method is going to work is it's quite hard to track two things moving at the same time. So the way we're going to get around that is we're going to try and keep one of the objects stationary. So in this case, I'm choosing to keep up the particle B stationary. So obviously the velocity of particle B must be 0r plus 0j. So how do we do that? Well, we're going to take this function over here, this position, this vector equation, and we're going to subtract the velocity equation from it. So we're going to subtract the velocity equation of B from it. And obviously what we do to one, we have to do to the other, because we have to keep the relative position of A and B the same. So what I'm going to do is I'm going to take my vector A, and I'm going to subtract the velocity of B from it. And that gives us this resultant here, because we're trying to track A relative to B. And we're going to do the exact same thing to B. And what you'll notice is that if I take vector B and I subtract its velocity function from it, we end up with just its initial position of 40 and 40. So essentially that means that the position of B is now stationary, and this is how the particle A is going to move around that position over there. So what you will find is that the direction of this one here will change, because now we're going to keep the vector B stationary, or particle B stationary. So I'm just going to change vector A a little bit. Now I'm just drawing generic lines here. I'm just showing that the line does change. That's not the actual line that we're looking for. So that's RA, and that's the direction that that particle is going to be traveling in. And now B is just a stationary point, because the velocity of B is now 0. And what we should also understand is that the minimum distance between any 2 points is via a straight line. And in this case, the straight line is going to be the normal line or the perpendicular line to the vector equation of A. Now, I'm going to call the time that particle B is perpendicular to particle A, I'm going to call that time lambda. That's just to distinguish from that time there, that's any time. I'm going to say that at a specific time lambda, that's where particle A is going to be. And at that point M, that is the minimum distance to B, because obviously if we go off at any angles, we're going to travel in a much larger distance. So we want to keep that distance as small as possible. So at time lambda, it's going to be the particle A is going to be at point M, which is going to be the minimum distance. Next, what we need to do is we need to set up some sort of equation to help us solve this. So I'm just going to draw two lines now. So this is going to be vector M, or OM, and this is going to be vector OB. Obviously, we're going to look to go from M to B or B to M. We want to figure out what the length of this green vector is going to be. So the way we're going to do that is, if we want to go from M to B, I can go backwards along this point here, and then we can go up to B. So if we're going from M to O, remember M is a point on the yellow line, which is the position vector of particle A. Because I'm going in the opposite direction, we're going to take minus the position vector of A. So that's what I mean there. If this is the position vector of A at lambda, okay, because we want to go in the opposite direction, I'm going to use the negative of that, plus OB. OB is just the position vector of B, which is 40, 40. So if we're going to go from M to B, we're going to go down this vector, and we're going to go up this vector, and we're going to add those two vectors together. So this is what we end up with. But we also know that the dot product of MB with the direction of A, because they're perpendicular, the direction vector of particle A and the direction of MB must be perpendicular, so the dot product must equal 0. We also know that the direction of A is 7 and 8, because remember we're using this equation here, not this one up here, because this is before we subtracted and we made B stationary. This is the position vector of A after we made B stationary. So this is the new direction of A. And we know that the dot product of this direction with MB must equal 0. So what we end up with is, when you simplified MB out, you would have had 30 minus 7 lambda and 10 minus 8 lambda. And if the dot product equals 0, expanding out the first component times the first component plus the second component times the second component, we end up with this equation over here, and we're going to solve for lambda. What you'll notice is that we ended up with the lambda is 290 over 113. In the calculus approach, we also ended up with a time of 290 over 113. So it's not surprising that the time is the same, because it's the exact same question. We're just looking at it from a different approach. Now we need to figure out what the length of this line is here. So we can substitute this lambda value back into my MB vector. So when we do that, when we substitute this 290 over 113 into our MB vector, we end up with these two fraction components. Now, we actually wanted to find out the length of MB. So this is the vector of MB. That's the position vector of MB. What we actually want to find is the length of that. So how do we find the length of a vector? Well, we just take the modulus of it. So if we take the modulus of MB, that's the first component squared plus the second component squared. And when you do all that, you end up with 170 over root 113 over 113, which is the exact same answer that we got in the calculus section. Now I'm sure you've already noticed that this method is a lot more involved with vectors. It's not my go-to when I'm solving these types of problems. This is just a visual representation of what we're doing. We're just trying to find the minimum length of MB.